Hello, young chemists. I am here on Thursday afternoon, and I wanted to just give you a little bit more before we break for the weekend and call it all good. We have a lab coming up on Monday, our quiz is on Tuesday. You'll notice when you look at the exercise document that we also have some assigned questions out of Chapter 10. We haven't talked at all about Chapter 10 yet. Chapter 10 is more about states of matter, physical changes. So I wanted to just give you a little bit of background on the physical changes. Some of it is going to, maybe all of it will look familiar to you, but just so we are all together on it. Remember that when you have substance changing temperature, we'll calculate the amount of energy required for that change, or given off by that change, with Q equals mc delta T. We only use this equation when we have a temperature change. There are some changes that don't involve temperature change. You'll see those in a moment. But so you want to remember that only when you have temperature changes do you use Q equals mc delta T. Now, when you have a phase change, like when a solid melts, liquid boils, that kind of thing, the temperature is not changing during that process. And it takes, like if you think of an ice cube on a table, it takes a long time for that ice cube to melt. So during that entire time that the ice cube is melting, it's gaining heat from its surroundings, and it's heating and heating and heating. But it's not going up in temperature. That ice stays at 0 degrees. When it melts down to a liquid, as a liquid it can raise in temperature, but during that phase change, the ice itself is steady at 0 degrees. And the same thing is true for a pot of water. If you boil a pot of water, it takes a long time for all the water liquid to change to a water vapor. But you can stick a thermometer in that, the temperature stays constant on 100 degrees Celsius, or close to it, and it doesn't change, it just stays there at that temperature. So that's what I'm saying here, is during that phase change, the temperature's not changing, but we're still adding or removing heat. And so, I know that we do this in Chem 1, so this is not a big surprise. The amount of heat required to melt a solid is calculated with this formula, Q equals heat of fusion times moles. The heat of fusion is a constant, just like the specific heat is a constant. Heat of fusion is defined as the amount of heat required to melt a mole of a solid. So just one thing that's a little bit of a pain about these equations. This one involves the mass of a substance, where this one you have to convert the mass into moles to be able to use it. So just be aware of that. And know that the heat of fusion usually is given in kilojoules per mole, where this, the unit of energy, is joules, because that C term is joules per gram degree Celsius. So be aware of that and use the right units when you're using these equations. So melting a solid is going to involve this equation. If you have a liquid that's boiling, you're going to use this equation. The Q is the heat of vaporization times mole. Now the heat of fusion and the heat of vaporization are not the same value. It takes more energy to boil a liquid, even 1 mole of a liquid, than it does to melt 1 mole of a solid. Both of those would be considered endothermic processes, but they're not anywhere close to the same. It's about 7 times more heat of vaporization for water than it is heat of fusion. So just know that you have to make sure you use the right constant value. And the problem would have to give you these values. It's not like you have to know them or come up with them. You'll know what they are from the problem and just plug them in. But the heat of vaporization, same thing. It's in kilojoules per mole. So it's the same as the heat of fusion in terms of its unit. On the next slide, there is a question taken from the book. I just want to kind of walk through it with you so that you know what to do when you get there. This is from the assigned problems in Chapter 10. And this is a super obnoxious problem that involves all 5 parts, all 3 states of matter, and all 5 of the different areas or regions of changes that you'll see. If I could just go back for 1 second, too. I've shown you just the endothermic processes of melting a solid going to a liquid and then boiling liquid going to gas. Both cases we have to add heat. The opposite processes will use the same values. If we have a liquid that's freezing, Q for freezing, we would consider that an exothermic process because we have to take heat out of the liquid to get it to freeze. So Q of freezing is going to have the same amount of energy involved, just be the other direction. So it's negative heat of fusion times moles. So melting is heat of fusion times moles, freezing is negative heat of fusion times moles. Same amount of energy. Whoops. Okay, the other thing is for the condensation, the opposite process to vaporization is condensation. So Q of condensing is the heat of vaporization times moles. Do you think I had to tell them that, Amber, or would they have figured it out?
Tell them what?
That.
I don't know.
You don't
told
know.
them.
All right, well, I told you. So you may have problems in the book that ask you to go the other way. I just wanted you to see those, and they're just negative processes. So, oh, I didn't put a negative sign in there, did I? Negative. All right, so then we get to this one. Let's take a look at what it says. You have a quantity of, or what quantity of heat would you need to take 500 grams of ice, fairly big sized chunk of ice. It's negative 20 degrees Celsius right now, so the water is in the solid form. You need to heat that up all the way through all three physical states until you have steam at 250 degrees. Now, one way that we use to just describe and help us to organize this information is what I call a phase change diagram. And I have it kind of hidden here, which I'll bring out. So we see that we're starting at negative 20. Here's our 0 mark. 0 is the flat area where the temperature's not changing, the melting process is happening. So I got negative 20 degrees is my starting point. So I start there. As I add heat to ice at negative 20, it will raise in temperature until I get to that phase change, at which it will level out, not change in temperature, while it melts. Once it gets to 0 degrees on the liquid side, so notice that you can have ice at 0, that would be right there. You can have liquid water at 0, it would be right there. And it does not, it's fine that you can have both physical states at the same temperature. That's what happens at a phase change temperature. So from 0 to 100, we're still adding heat to it. And then going from liquid water at 100 to water vapor at 100, that takes a certain amount of energy. And it's not to scale, but do notice that I made the boiling plateau much bigger than the melting plateau because this always takes more energy. When you're boiling a liquid, you're breaking the particles completely apart from each other. So it will take more energy. And then we're going up all the way through the gas phase. And this is not to scale at all, but I'll just make my 250 degree mark here. That's kind of pathetic, really, but you get the idea. So the question is, what quantity of heat? I want to know how much heat it takes to get from there to there. Now, the amount of heat is along this axis. It's like we're adding heat through this whole process. There's some areas where we're adding heat, but the temperature's not changing. That's there and there. So I'm going to mark these different areas off with numbers. I'm going to call this area Q1. That's where the temperature is raising and the water is a solid. This area, flat area, is Q2. That's where the solid is melting to liquid water. Q3 is liquid water increasing in temperature until it boils. Q4 is the boiling of the water. And then Q5 is the steam heating up. So we have 5 Qs that we have to find for this, and they're all different. We have to find them and add them all together. So I'm not going to do the entire problem. It is number 99. You can look it up on the solution guide. But for Q1, we have a temperature change. So Q1 is going to involve using MC delta T. Be careful, this is ice. Ice has a different specific heat than liquid water does. You would not plug in 4.18 for that one. It's 2.1, I think. But the book will have that. And so you'll need that C value. The delta T would be 20 degrees. You're going from negative 20 up to 0, so that's a 20 degree change. The mass that you give the mass. So that's Q1. That takes care of that Q. Q2 is going to be the melting of ice, and that's where we're going to use the heat of fusion times moles. Be aware, this first Q is in joules, the second one's in kilojoules. And then we're going to go on to Q3, another MC delta T where it's liquid water, and we'll use 4.18 for the C value as water. And then Q4 is our boiling, so we're going to use Q4 equals heat of vaporization times moles. And then Q5 is where it's steam. And once again, steam has its own specific heat. So Q5 is MC delta T, because the temperature changing there, so we can use MC delta T. So you're going to have 5 Qs, get them all in the same unit. I would suggest that because it's such a big quantity, you're going to wind up changing to kilojoules for all of them. It'll be more convenient numbers. Add them all together, you get the answer. So yeah, much of the chapter 10 questions they're not all as comprehensive as this one. This one is crazy. That's why I wanted to show you, because it has all of the different regions on a phase change diagram. The last thing that I want to talk to you about is the lab that we're going to do on Monday. It's a Hess Law Lab. You're going to have to use coffee cup calorimetry. I'll be back. With our fancy setup, you remember this. You're going to put the amounts given in this description here. You don't have to write this down right now. This will be up on Monday. And so for the first reaction, you're going to react magnesium with hydrochloric acid. Notice I'm not giving you what the products are. You have to figure it out. But I'm telling you how much of each to use. So you're going to want to know how much energy is either given off or taken in. It's not obvious from what's reacting, I don't think. So yeah, just watch your thermometer. Make sure you wait until your temperature change is done. Then clean everything up and do another equation. You're going to do magnesium oxide with hydrochloric acid with those amounts. Now it says about 5 grams. It doesn't matter. It can be around 5 grams, because eventually down here we're going to find out what the delta H was per mole of magnesium oxide. So it doesn't matter. If you use more than 0.5, you'll have a little bit bigger delta T, but then you'll divide out a bigger mass or number of moles. So just be around 0.5. Now you're finding with calorimetry what the delta H of both of these reactants are. There's two. I said delta H of reactants. The reactions. You need to actually look up the delta H of a third reaction, and that is just the heat of formation of liquid water. You need to come up with a chemical equation and the value of the heat of formation of liquid water. That gives you 3 different delta H's, 1, 2, and 3. 2 of them are experimental. 1 of them you'll just use the theoretical values for, use the heat of formation table. I asked you to put a box around or highlight the definition of heat of formation. This is a great time to go back and review what that is. Because ultimately what we're trying to do in this experiment is we're going to use these 3 equations that we came up with, the delta H's for them, and use Hess's law to come up with what is the delta H, well, the heat of formation of magnesium oxide. So you're going to need a chemical equation for the heat of formation of magnesium oxide. That becomes your target equation. And you have 3 given equations to work with. You'll need to manipulate those equations just like I showed you in class today on Thursday, and figure out what the heat of formation of magnesium oxide. That's our experiment. And so you'll do the experiment on Monday. You'll do those calorimetry experiments. And then, of course, you can do that during class on Monday, too. You'll need a textbook. And you'll have until Wednesday to come up with that. It'll be a normal write-up. I think that's good. You have the rest of the hour today. Hopefully I haven't taken long. I don't know how long that was. How long am I doing there, Andy?
14 minutes.
14 minutes. So you got about a half hour or more to work on. I would really suggest, I know it's Friday, work on the problems while one another is around, and good luck with that. I know the test or quiz is not until Tuesday, but you'll be really glad to knock some of these out. So have a nice weekend.
Thanks. That was really boring.
Did you turn me off?